Okay, we are about to start. So we're delighted to have Boris Hanin. Boris was a student at Northwestern under Steve Zeldich. He had positions at MIT and UT Austin and Texas A&M. And now he's an assistant professor at Princeton. And let's welcome Boris.
Thanks, Mike. It's best not to confuse UT Austin, Texas A&M, depending on who you're around. No, thank you very much for the invitation to be here, for organizing this. I've had a lot of fun listening to the various talks and talking to people, so this has been great. And I'm quite excited to share with you all kind of a circle of ideas that has been fascinating to me the last couple of years. I call it scaling limits of neural networks. Let me just say that this is some set of kind of ideas for how to use mathematical techniques coming from statistical physics and random matrix theory and so on, both to kind of understand what neural networks are doing and how learning is proceeding, but also with a, I think, more or less direct view to impact the practical use of neural networks. I'm going to try to kind of walk you through all that. But as I go, just feel free to interrupt me. Stop me. I don't mean to save all the questions for the end. And I've almost certainly prepared too many slides to get through anyway. So it's a bit of a lost cause. Okay, so I don't want to assume that everybody already knows what a neural network is and how machine learning works. So I'm going to slightly rehash the talk from earlier this week, just so that we're all on the same page of kind of a crash course on neural networks and what I think modern machine learning looks like in a nutshell. Okay, so first of all, at a very high level, a neural network is a parameterized family of functions. And this is the very simplest kind of neural network. These are called fully connected feed-forward networks. So let me just walk you through sort of how the output is computed. This is the output as a function of the input x. So basically x is an n0 dimensional vector. That's my notation for the input dimension. And we're going to compute the output by processing x through a sequence of hidden layers. So the first hidden layer is very simple. Well, they're all simple. You just multiply x by a matrix W1. It takes you from Rn0 to Rn1. And then you apply to each component of the result the same nonlinear function sigma. Okay, so that's one layer, basically linear transformation, then coordinate-wise nonlinearity. You do this capital L times. L is the number of layers, also known as the depth of the neural network. And then the output is just a linear readout of that final hidden layer. Okay, so that's my notation for a fully connected network. And when I write this parameter vector here, theta, I just mean the entries of all the W matrices. Okay, so somebody hands you the n's and hands you the capital L and the sigma. That's like the datum of a neural network. And then you get to vary the parameters theta. Okay, so I tend to think of a neural network in one of two ways. So this is maybe how a computer thinks about it on the left. There's just a long list of parameters. This is a very high dimensional space. You might have millions or billions or trillions of parameters in practice. And you can vary theta. And as you vary theta, you get different functions that map x to zl plus 1 of x. But because the map from the parameters to the outputs is rather complicated, I sort of prefer to think of the kinds of functions you can get in this slightly cartoonish, manifoldy way. Okay, so you move theta around and you can hopefully get different and interesting functions out. Okay, so that's what a neural network is, and this is how I visualize it. And then how are they actually used in practice? Okay, well, I'm just going to give you a very kind of short rendition of that. So the typical use basically has 3 steps for me. Step number 1 is you go out and you observe something about the world. So you observe a bunch of inputs xi, this is where the x's go, and then some outputs f of xi. F is a function that you don't know, so but you have some examples for. Maybe xi is like the state of the stock market on day I, and f of xi is like the return on your portfolio on day I plus 1 or something like that. Okay, so you'd love to have a formula for f, but all you have is some historical data. And you hope that f, or some good approximation to f, lies somewhere in the space of functions you can compute with your neural network. Okay, so we'd like to learn an approximation to f. And how are we going to do that? Well, step number 1 is to be a bit humble and to say, well, we have no idea exactly which setting of parameters at first corresponds to this f. So what we're going to do is we're going to choose the initial setting of parameters at random. Okay, the way it works, and I've sort of indicated the generic sort of PyTorch default way of setting your hyperparameters at the start of training, is you put a very simple probability measure on the space of parameters. Think like each component, every weight in every matrix is just IID Gaussian. Okay, so that's why I've kind of indicated a simple distribution here as a bell curve. But then since the map from theta to z's is rather complicated, you start by sampling your initial function from a kind of complicated and interesting measure. And I'll say something about this measure as we go on in this presentation. Okay, so obviously this function that you start with at the start of training has nothing to do with the function f because you haven't used your training data yet. And so that's kind of the final key step, which is you iteratively improve your guess for theta by some version of a greedy local search, some version of gradient descent. So if you're at some value theta t after t time steps of optimization, you take a step of size eta, eta is sometimes called the learning rate or the step size, in the direction of the negative gradient of your loss. This is like an empirical risk over your data. It measures how well you're currently fitting the training data that you see. Okay, so somehow it's easy to draw the picture, it's just hard to prove a theorem. You do something in the parameter space, and this corresponds to something in the space of functions. And hopefully, okay, just for fun, I drew it in a slightly non-trivial topological way, kind of. Hopefully you get to the function that generated your data. That's pretty much the dream of how neural networks are used. Okay, so let me just pause for 1 second and make sure the notation is okay. This is the basic notation I hope to use. It's okay. Okay, great. Well, if Mike is happy, how can I not be? Great. Okay, so now I want to tell you about the other part of the title. I said something about scaling limits. So I've just recapitulated kind of at the top what a neural network is for me. So when I mean scaling limit, I mean the attempt to analyze learning with neural networks in the regime where all the parameters that are kind of large in practice could actually be large. Okay, so in the real world, we have many training data points. We can have very high dimensional data. We can have a deep network. We can have a wide network. We can have a large compute budget. There are many things that could be large parameters in practice. And I'd like to understand what happens when they're not just large, but when they're infinitely large. That's kind of the mathematical statement of the problem. Okay, so especially if you're not really mathematically oriented, you might say, why do you care about infinite size data sets, infinite size neural networks? Wasn't it painful enough to just have large neural networks and large data sets? Okay, so let me offer kind of two motivations. So motivation number one is a kind of theoretical motivation, which is that a kind of, I think, theme across probability and statistics and machine learning and physics and everything is that if you have a large parameter, very often, at least if you do things judiciously, when you take that parameter to infinity, things become simpler rather than harder. Think about things like the law of large numbers or the central limit theorem or the asymptotic distribution of eigenvalues of a random matrix or things like this. So the hope mathematically on the theory side is to have simplified descriptions of learning that you can then actually analytically analyze and say something about. Okay, that's kind of the theory person talking. But then what I hope to convince you of is that there's an equally important practical motivation. And this is what's called hyperparameter transfer or hyperparameter tuning, which I hope to explain right now. So one of the big disasters in actually using a neural network in practice, okay, this is what people don't always tell you about because it's painful and doesn't obviously lead to a success, is that you have to choose a seemingly infinite number of hyperparameters. Okay, when people say hyperparameter, they mean not the trainable parameters of the neural network, but all the other things. So there are hyperparameters that come from the architecture, for example, like the depth and the width of the model, or the number of self-attention heads if you have a transformer and so on. You have to tell the computer that. Then there are hyperparameters in your initialization. How exactly do you start training? From what measure do you select your parameters? There are hyperparameters in the optimizer. How do you choose your learning rates and so on? And if you don't make these choices well, all that money you spent on your GPUs and collecting data and all that, it's all going to go down the tubes. That's the really sad truth. And so this kind of leads to kind of this practical tension, I would say. On the one hand, there's like the extreme sensitivity, at least often extreme sensitivity, of the actual performance of your model to your setting of hyperparameters. On the other hand, the larger your model is, the more expensive it is to just try different hyperparameter values. Okay, so let me, just because I can't help myself, let me show you a fun video. This video was made by a researcher named Joshua Soldikstein, who many of you might know. He's really amazing. He is at Google. And okay, so here's what the video is. At the very least, it's just a fun video. But okay, so what we're looking at here is he's training a one hidden layer network, very simple model. And on the x-axis, he plots the learning rate for the first layer. And on the y-axis, he plots the learning rate for the second layer. And here, each kind of learning rate in the two layers gets a value in the pixel space, and that's how well the model performed. Okay, and the most highly performant models are the ones at the interface between the red, the orange, and the green-blue. So the point of this picture is that if you were to try to find a good setting of this hyperparameter value, and I don't want to think about how much compute was used to make this plot, okay, then you're trying to optimize over this like very non-smooth landscape. This is this extreme sensitivity coming up.
It's all the same initial condition.
Yeah, so I think they do the same initialization, they freeze that seed and they just, or maybe they average over a couple of seeds, this kind of thing. So this is kind of what this is like a visual illustration of the sensitivity of the final trained model to the hyperparameters you're going to choose. So doing this is obviously a disaster, okay? Eventually it becomes pixelated. Even Google only has a finite amount of compute. Okay, so let me figure out how to turn this off.
But this is saying that the 10th decimal place of these theta values is important.
So
or those are not the hyperparameters.
Those are not that. So yeah, it's not the thetas. That's the step size in your optimizer.
So it's the depth and width and this sort of thing. Feedback loops.
It's just the learning rate, just the coefficients in that dynamic.
Yeah. So you know that was literally just a two-dimensional slice of what's the learning rate in the first layer, what's the learning rate in the second layer, and even that turns out to be rather complicated. I don't know how to get rid of that. Should not.
But then it looks from the picture that it depends very sensitively, right?
So indeed. So
does that make it hopeless to make a good choice?
Well, so I think my point of view is it's not that it's hopeless, it's just computationally expensive.
I'm kind of surprised how much of that survived the averaging of.
So I believe there was some averaging, but so my point is just to illustrate that you do in practice see that it's important to choose your hyperparameters carefully. And it's prohibitively expensive to do so at large scale. And so this gives rise to a whole kind of field, I would say somewhere between theory and practice of deep learning, called hyperparameter transfer. So here's the dream. Someone comes to you with a big neural network. It has 1 trillion parameters, and they say, I want to find the best learning rate. And they say it's too expensive to experiment. That's basically what happened for GPT, for example. So what you'd like to do is you'd like to take your big model and make it much smaller, 1,000 times smaller, 1,000,000 times smaller, and have a much smaller model in which the optimal setting of the learning rate for the small model is actually the same as the optimal setting of the learning rate for the large model. And you just numerically find it for the small model. Okay, that's what hyperparameter transfer is. You transfer the hyperparameters from small models to large models. No one said that the two models will perform the same. The large model is going to do better. That's just a question of finding the right hyperparameters to do your optimization. Okay, so I think at first blush, it may seem like a pipe dream. What does a big model have to do with a small model? But I'm here to tell you that it's possible. Okay, there's some mathematical principles for this, and that's what I want to go over. So let me just show you an example. This is jumping to the very end, because I don't know if I'm going to get to the end, frankly. This is the kind of thing that came up in a paper that I wrote with some of my colleagues here from Harvard, with Cengiz Talban and his group, and some of my postdocs and students. So the setting here is we take a very simple model. We take a residual network, a ResNet, that's fairly deep, and we train it for 20 epochs on a standard benchmark data set in computer vision called CFAR10. Okay, so the different colors and dotted lines here, the legend is on the right. So the different colors indicate models of different depths, and the different dashed or solid lines indicate models of different widths. Okay, so the difference between the largest model, which is down here and performs the best, and the smallest model up here and performs correspondingly the worst, is roughly 300 or 400x in the number of parameters. Okay, so we didn't try very hard to push this, but they're rather different models. And what you see is the following. Using the kind of scaling that we propose in this paper, what you find is that if you had just trained your smallest model on a bunch of different possible learning rates and said, aha, this was the one that was the best, in the sense that it got the lowest training loss after 20 epochs. That's a more or less random criterion. It's also the best one for all the other models. Again, the training loss goes down, but the best learning rate stays approximately constant. That's the kind of thing that you hope for from principles for hyperparameter transfer and tuning. Okay, so this was some comparison against what the kind of previous state of the art is. Let me not go into it too much, but I'm just saying this is like the aspiration.
Quick question. So fixing the learning rate for the whole learning process.
Yeah, here we did not do schedules. But in fact, the way we approach hyperparameter transfer, the entire schedule will transfer. So that's in fact necessary for it to be practically useful, because scheduling is key. Yeah. Okay, great. So this is the dream, and I want to now tell you on the very simplest baby example why this should conceptually be possible. Okay, just because a philosophical question, what could possibly be working here? So let me take us back to the 1950s. Okay, not that I would know what the 1950s looked like, but I can imagine. Imagine in the 1950s, all we had was kernel ridge regression. Okay, maybe that's false, but that's how I think about it. So let me set up the deliberately as vanilla as possible problem. Okay, so you observe a bunch of X's, and they're all sampled ID from an isotropic Gaussian in D dimensions. And then you observe some responses Y, which are just the secret vector beta transpose X plus noise. And you have a little n of these samples. Okay, so there are basically two large parameters in this problem. There's the number of samples you observe and the number of features, i.e. the dimension of each sample. Okay, so here you are. Imagine that you're at this point in your parameter space. You have 1 million samples in 10 million dimensions. That's like not totally unreasonable. And you want to understand how to do learning. Okay, well, how did we do learning before neural networks and before everything? We did ridge regularized regression. So I'm going to say, I'm going to fix a hyperparameter lambda, and I'm going to consider the optimal predictor or optimal setting of parameters theta star depending on lambda, which just minimizes the empirical risk over the data plus lambda times the norm squared of my parameter vector. Okay, there's an exact well-known formula for this thing. The learning in this sense is not hard. Okay, so this is a problem in which I have one hyperparameter. Think of this as the analog of the learning rate you're trying to use. Okay, and what's the goal? The goal is to find the best setting of the hyperparameter. I want optimal hyperparameters. So for me, that means I want to find that value of lambda, which minimizes the out of sample risk on a new training data. Okay, that's my training. So how could you do it? Well, a practitioner might say, no problem. I'm going to do cross-validation. I'm going to try a bunch of different lambdas. And then I'm going to simply choose the one that works best from my numerical procedure, and I'm going to do it. But I'm here to tell you, imagine that you just don't have the computational resources to do it. Okay, you might scoff at these numbers here, but just replace this by 10 to the 12th and 10 to the 13th. Okay, and now no one is kind of laughing. I think you can't really do cross-validation in that setting. Okay, so the theory person comes in and says, no problem, theory is going to save you. So how's theory going to save you? You're going to say, attempt number one at having theory save you is maybe, just maybe, the optimal value of lambda star transfers, i.e. is approximately constant over vertical slices. Maybe that's a conjecture. So let's see if this is going to be true. So I fix the number of samples, I set the number of features to infinity, and you're going to get a perfectly well-defined mathematical model, but it's very sad. You're going to get that lambda star is infinity up here, right? You're in an infinite dimensional space. You observe a finite number of examples, and therefore you haven't seen anything about your vector beta at all. So you just want the zero predictor everywhere, and you just got fired from your job. Okay? If you make zero as your prediction always, it's really sad. So this is an example where there was a well-defined scaling limit, but it was not a good scaling limit in the sense that this infinite model simply was not close for practical purposes to the model that I started with. Okay, so you say, no problem, I have another large parameter. I'm going to take that one to infinity. I'm going to fix the number of features that I have, the dimension which everything lives, take more and more and more and more samples. Okay, you'll again get a perfectly well-defined mathematical limit, and you can calculate lambda star exactly, and it's going to be finite, and it's just going to have to be about regularizing the noise that you see here, these epsilons that you saw in your data. But again, that value of lambda star will be very far from the optimal value of lambda star in your actual setting that you're interested in. Okay, so again, if you didn't get fired, you at least didn't get a promotion. It wasn't as bad as predicting zero everywhere. So what's the problem? The problem is that your hyperparameter simply is not transferring across vertical or horizontal lines. Okay, so what's the resolution to this? Well, the resolution is very simple. You say there's a non-commutativity. D and N going to infinity don't commute. I have to basically blow up this corner of the phase diagram, so to speak. And so what's the issue? Well, the key realization from random matrix theory or high dimensional probability, however you want to say it, is that, look, there are two key matrices that make up the predictor of theta star. There's the sample covariance XX transpose, and there's kind of the cross covariance XY between the inputs and the outputs. And the spectrum of these matrices, that's what you have to think about when asking how well this theta is going to work. But the spectrum of these matrices does not depend independently on D or on M. Yeah, like a classical fact, think of the Marchenko-Pasteur theorem, is that it depends on their ratio. Okay, so if you want to approximately preserve the statistics of your predictor theta star, what you have to do is you have to realize you have to go in these lines of constant slope away from the origin in your diagram. Okay, so mathematically speaking, you can now send D and N to infinity together at a fixed ratio. Here my ratio was 10. And you can calculate exactly what value of lambda star you're going to get here. And this value of lambda star at D over N equals 10 will in fact be very close to lambda star in practice. Okay, so this is what a theorist would say. Here's my correct scaling limit. And in the scaling limit, I can do analytic calculations. But the practitioner says, who needs your scaling limit after all? Instead of making your model bigger, why not simply make your model smaller? Okay, so instead of going up this line, I'm going to go down this line. If this was too much for my computational abilities, I'm going to make both N and D 1,000 times smaller. Then I'm going to do cross-validation down here, and that's going to have to be good enough as a way of estimating the best hyperparameter choice in my actual model. Okay, so that's kind of the duality between the scaling limits that a theory person is interested in and the kind of hyperparameter transfer and tuning that you might be interested in practice. They're really the same question. Okay, let me pause for just a second. See if there are questions or comments about this. Because I'd like to now start talking about neural networks, but this is like the philosophy of what's going on. You have to understand how to take limits so that the infinite size model is actually close to your finite size model. And then you can hope to do some sort of interesting transfer. It's okay. One thumbs up. Better than no thumbs up. We continue. Okay, so let me now return to neural networks. And because I can't help myself, let me tell you what my favorite example of non-commutativity of limits in neural networks is. Anyone who's ever talked to me has already seen this example, but okay, life is tough. So let me say, in addition to the number of samples and the number of features in a neural network, there's also the depth. That's like the new thing in some sense. So let me look at the very, very simplest example of non-commutativity for neural networks. And here, what I'm going to look at is what's called a deep linear network. So I've removed the nonlinearity sigma between my weight matrices. It's simply the identity. So my output is just a product of matrices times the input. And I'm not going to be interested in training or anything at all. I'm just going to be interested in the initial measure you get before you train, when all your parameters are random. Okay, so every entry of these n by n matrices, I simplified my life and made all the widths the same large number n. All the entries are just IID appropriately scaled centered Gaussians. And I'm going to make the norm of my input vector x equal 1. Okay, so the first thing to say, and this makes my mathematical heart happy, is that products of random matrices, which is what we're studying in this very simple model, have been studied forever. Okay, there are plus infinity papers on a variety of topics on random matrices and these products in particular. And the papers basically come in two regimes. Okay, so one regime is you fix the depth of the network, which is simply the number of terms in your matrix product. And you let the size of the matrices go to infinity. That's what's usually called the free probability regime. That's a beautiful subject. Everything about universality comes from here. Maximum entropy distributions over eigenvalues, singular values. It's kind of this canonical subject in high dimensional statistics and probability. Okay, so that's very nice. But then there's an equally important and equally well-studied regime where you fix the size of the matrices and you let the number of terms in the product go to infinity. So this is like about the study of Lyapunov exponents for random dynamical systems. It's the realm of what's called the multiplicative ergodic theorem and so on. So there's these kind of two regimes and they're very, very different. And as the picture already suggests, the two limits as n and L go to infinity don't commute. Okay, so this is going to be towards what kind of scaling limits can you even expect for neural networks at all? Okay, so let me show you this non-commutativity on the simplest possible observable. Okay, just fix my input vector x. I take these w's to be random and I just compute the norm. So this is just a random number, scalar number. All right, well, let's try to calculate what happens in the two regimes. So let me fix first the depth of the model. and take the size of the matrices to infinity. Okay, what are you going to get? Okay, well, you have to scratch your head for a minute and digest the notation and all that. But the key observation is that with this exact scaling that I took for the variance of the matrix entries, each of these large Gaussian matrices is very close to preserving lengths and angles. That's how the normalization works. And okay, I have a couple of them, but I only have 17 of them or whatever. My L is fixed. So the whole product, as n gets bigger and bigger, is closer and closer to preserving the norm of the input. And so as a result, because the norm of the input was 1, what you can easily show is that almost surely you get 1 in this free probability limit. Okay, that's very nice. Okay, very good. So now let's try to calculate what happens when you fix the matrix size and let the number of terms go to infinity. I want to go that way. So question, especially if someone hasn't seen it, does anyone know the answer? Yeah. No. So what's the other option?
I think it's infinity.
So you get 0. All the singular values will be less than 1. And there's more and more and more.
I would think if you stretch the vector in some random direction, and then it's more likely to have a large projection with the next larger singular.
Well, but they're independent, they're incoherent from one another.
Yeah, but once something is stretched, it's likely to line up with the next larger singular value.
Yeah, so that's almost the right intuition, except that it turns out that on average you slightly compress them.
Oh.
And so you go to 0 instead of infinity.
All right, I got the sign wrong.
Precisely. Yeah, so indeed, like there's a famous result which says if you take this matrix product and you raise it to the 1 over L power, and then you take L to infinity, all the singular values are between 0 and 1. So if you then raise it to the L power, all the singular values go to 0. That's okay. So you get 0. Okay, so as promised, this is the simplest example, or I think the simplest example of width and depth non-commuting. And so the question is like, what happens in here? Someone actually comes to you with a neural network, has some depth, it has some width, and you want to know what to think. Well, okay, I was always taught that a good talk has to have several ingredients. It has to have a theorem, it has to have a picture, it has to have a calculation, and it has to have a joke. And the key thing is the theorem and the joke have to be different. Okay, that's my joke, if you hadn't noticed. All right, very good. So let me do the calculation. Okay, the theorem is coming, but the calculation is here. It's the only calculation I know how to do in one slide that I think is illustrative here. So let me show you a neat trick for understanding this particular random variable. You can do it exactly non-asymptotically in this case. Okay, so what do? You want to compute the norm of this matrix product times x. And the key idea is not to think too hard and just multiply and divide by the norm of W, the first matrix, times x. Okay, and then what do you observe? Well, look, W1 times x is a standard Gaussian vector. X was a unit vector after all. And the direction of a standard Gaussian vector is independent of its norm. Right? And its norm has a chi-squared distribution or a square root of a chi-squared distribution. So what you find is, since W2 is rotationally invariant, you may as well take this unit vector to be x again. And the distribution of this object is independent. It's a scaled chi-square distribution with a square root because I haven't taken the square root. Okay, so I went from L matrices to L minus 1 matrices. So I'm very happy. And I apply this L minus 1 more times. So what do I learn? I learned that there's this kind of, I think, really beautiful exact distributional formula for this random variable. And what is it? It's a product of chi-squared random variables normalized to have mean 1 and then a square root. Okay, so I think this formula is actually kind of beautiful in its own way. It's a very special case, obviously, but it shows you how N and L fight each other. Okay, so N tries to thermalize you. It tries to send everything to its mean. 1 over N times chi-squared N concentrates really quickly around its mean, which is 1. That's why we got that you get 1 in this free probability limit. But on the other hand, you have a product of L such things, and the L exacerbates the fluctuations. Okay, so the L sends you away from the kind of mean field kind of limit, and you get something totally different. Okay, so let me just complete the calculation by doing the only sensible thing, which is taking x sum log. Okay, I just rewrote this, and in the exponent you have a sum of IID random variables. And so if you want to understand what happens when L is large, you can just apply the central limit theorem in the numerator. Okay, so I do this, and you should just trust me that I calculated the mean and variance of each of these correctly. And what you get at large L is you get e to a Gaussian with mean minus L over 4n and variance L over 4. Okay, so the TLDR is that the right parameter to introduce is the ratio between the number of terms in your matrix product and the size of the matrices. And there really is a one parameter family of scaling limits for this random matrix ensemble that kind of interpolates between the free probability regime and the ergodic theory regime. And what I want to say is, even if you don't care at all about neural networks, I think there are many beautiful and really fundamental open problems just on the random matrix side on this regime. I think about some of them, and okay, I wish I had time to think about more of them because they're really rather fascinating. Okay, so this was just meant to be a warm-up. I just wanted to indicate something about the non-commutativity, but it's a little bit sad because the whole point of neural networks is that they have those sigmas in here. At the moment, all you can do is you can compute a linear function of x in a kind of funny way. Okay, so let me say something about the nonlinear case. Again, let me just pause for 2 seconds and see if there are comments or questions about this. Yeah.
Just real quick, how does the variance of the matrix of the weights change the final term?
Well, okay, so this with this normalization on the W's, all the singular values remain bounded at large n. But everything is totally homogeneous on the W's. If you wanted to change the variance, you could just scale out the product of your variance changes in front.
This is like edge of chaos initialization. So if it's just a bit larger here in the different regimes.
Well, yeah, you want to stay on the edge. Like if you're going to take n and L to infinity, this is the only sensible thing to do.
Okay. So my question is, how does that exponential sum at the final one?
Yeah.
Does it change meaningfully if you have a variance, arbitrary variance to the weights?
Well, I mean, yeah, the short answer is this: if you change the variance by a constant c, you just get a prefactor of c to the L.
Where?
Like in front of, just because this is homogeneous, right? Well, c to the L over 2 technically. You just multiply each one of them by a square root of c to change the variance. Right? So yeah, it's not very insightful at this point.
Just a quick question. If you constrain all those W's to a determinant 1, was my original guess correct? It would go to infinity instead of 0?
Not obviously. So if all of them were orthogonal, for instance.
Well, then it would be 1.
Well, so indeed.
Yeah.
So
But if it's random, but the determinant is constrained, that keeps the spectrum. Well, it impacts the spectrum. I'm just guessing that it still goes to infinity.
I'm not 100% sure, actually, honestly. Yeah, I find it's a little subtle, and there are many open questions about like computing what happens in this regime, as a function of your matrix model.
Yeah.
So yeah, I'm not sure. Yeah.
So you stated at the beginning that the Gaussian is how PyTorch initializes the variance line. It may actually be uniform.
So what was important is just the variance. This is the Hanin normalization for the variance.
Just ask though. So would it be the same if it's a uniform distribution?
So yeah, okay, yes. So I proved the universality result in the sense of random matrix theory. You can have any distribution here, which is mean 0, variance 1 over n. It has a couple higher moments, and you get the same limiting answer. Just this calculation doesn't work. Then you need the rotational invariance on the Gaussian to make this easy.
But the same statement all of them.
Yeah, correct, indeed.
So sorry. So in physical terms, this says that like the deep nets, your random vectors are either going to completely blow up or go to 0 because of that n, which is the.
No. You have if L over n is constant.
But what's
Then-
the calligraphic n?
Oh, that's a Gaussian. Sorry, Gaussian
Oh,
means
sorry.
0. Sorry. No. So if L over n is constant, you get
Yeah, but as the depth goes to infinity, L goes to infinity, right?
Well, L can go to infinity, but L over n can remain finite. That's the point of the scaling limit. So the interpretation, which will be on the next slide, is L over n plays a role of the effective depth of the model. That's kind of the right way to think about it. Yeah, so in fact, let me state that, and then I'm happy to kind of have more discussion. So let me upgrade my model to having the sigma in here, because the sigma is key. And let me just summarize. Okay, I got very interested in these kind of double scaling limits of depth and width being large for these fully connected networks. And there's basically kind of the analog of the two regimes in the random matrix theory side. If you fix the depth and you let the width go to infinity, at least with this kind of initialization that I have, you get what's called the NTK or lazy or kernel regime, where neural networks become linear models. That's kind of a famous limit of neural networks, which is a little sad because the whole point of neural networks is that they're not supposed to be linear models. But then if you kind of fix the width of the network and you let the depth grow large, it was known that these networks are untrainable. And so the question was, what happens for these nonlinear networks? And the short answer is the following. I proved a number of theorems which basically say this. They say, imagine that the widths of your hidden layers are all proportional to the same large integer n. Doesn't have to be exactly equal, but proportional. Then just like the case of the product of random matrices, the right way to measure the complexity of your model, for instance, how far are you from being in this kind of linear model regime, is not L separately or N separately, but it's their ratio. It plays the role of the effective depth of the neural network. So for instance, if the effective depth of the neural network goes to 0, then even if L went to infinity, just slower than N, you're still going to be in this kernel or lazy regime. Okay? And so if you want to learn features, if you want your neural network to be nonlinear, this kind of analysis showed really for the first time that you need depth. That's the only way to learn features in this kind of precise sense. So feature learning suggests you want L over N to be large. Okay, but like the discussion we were just having also suggests, there's a price you have to pay, which is, remember, everything was exponential in L over N. So if L over N is too big, then what happens is you're not going to be numerically stable enough to actually do learning. So this gave a kind of exact solution to a numerical stability problem that people have been encountering for a long time in neural networks called the exploding and vanishing gradient problem. And it basically says if you measure the variance of your gradients at the start of training, they're going to be exponential in L over N. That's really what the theorem says. So if L over N is too big, your variants are either very, very large or very, very small, and you just don't make any numerical progress. Okay, so this is just meant to kind of build out the very simple-minded phase diagram for neural networks where, okay, we think about the width and depth being large, but in all of these analyses, the number of training data points is fixed. That's how these analyses go. And we already saw that the width and the number of training data points going to infinity don't commute. So it's like an interesting question, which I'm about to get to now. Well, can you say anything in a regime where the depth and width and number of training data points all grow? It's not clear what kind of limits exist at all. Okay, so let me just stop here for a second again, ask if there are questions. That's like the downside of slides. I thought about doing a board talk, but I couldn't bring myself to commit to it.
Put an expression for the effect of nonlinearity on that exponential term in the previous slide.
Yeah, so the way it basically works is, I sort of swept this under the rug. If you really want to go to large L, then you need to do what's called nonlinearity shaping. So your nonlinearity in every layer has to be close to the identity. Has to be 1 over L close to the identity. And although that looks kind of silly, what happens because you have L layers, you get an order 1 difference from the deep linear network. That's kind of the critical thing. And then like how big the difference is from the identity, the constant in the constant over L, that's what actually kind of comes into here. So it's like that constant times L over N. That's the kind of effect of the nonlinearity that survives essentially. Yeah. Okay, great. So this is some kind of scaling limits. Here you can't really use random matrix theory, at least in any way I know. I had to use techniques from like statistical physics, basically statistical mechanics, or kind of statistical field theory to kind of calculate the correlation functions of these random fields. That's the kind of thing that goes into a theorem like this. Okay, very good. So that was kind of scaling limits version 1. But now let me do scaling limits version 2. And so version 2 is a little bit sadder than version 1, but it's also a little happier than version 1 in a way I will explain right now. So at least for this version of the scaling limit, I actually just finished recently a paper for the nonlinear version as well, but it's like kind of requires its own talk to do it some justice. So I'm going to go back to the deep linear case. Okay, so I removed the nonlinearity here. And instead of learning by stochastic gradient descent, which is obviously what we do in practice, I was able to study together with my really excellent collaborator from MIT, a guy named Alexander Zlokapa. He's a PhD student in math there, learning by Bayesian inference. So instead of thinking of this as the initial distribution of the weights before you do training by stochastic gradient descent, you think of this kind of IAD Gaussian distribution on each parameter as defining a prior over your kind of predictions. And then you're going to observe a training data set, and the whole point of this analysis, you can let the size of the training data set grow together with the depth and the width of the network and ask what happens. Okay, so the theorem was like this. We observe a data set with n IID samples. We have just a mean squared error as our negative log likelihood. That's kind of the analog of having mean squared error as your loss function. And we do Bayesian inference at 0 temperature. So that means kind of like in the usual modern setup, you exactly fit the data. Okay, you enforce the condition that you fit all your training data points exactly. Okay, and what we found in this case, and I was extremely excited about this, I have to admit, is that this model of take this kind of complicated prior, it looks simple for each parameter separately, but the prior on the product of these matrices is rather complicated, right? Products of Gaussians are kind of complicated objects. And although they're somewhat complicated, you can still get exact formulas for the posterior. So you don't have to do anything asymptotic at first. You can write down the log partition function and write it down exactly in terms of a class of special functions called Meyer G functions. Okay, it doesn't matter. When I say exactly solvable model, I mean you can write down the answer in terms of a special function. That's more or less a tautology for me. And the reason I was excited by this is that 93.7% of Bayesian inference in practice is based on the fact that if L equals 0, you just have a single Gaussian matrix, and you have a Gaussian prior on your parameters, and you have a quadratic log likelihood, then the posterior is again Gaussian. And so you can exactly calculate it, and that's really useful for actually doing Bayesian inference in the real world. And in general, once you move beyond the case of models that are linear in their parameters, it's very rare to find exactly solvable kind of Bayesian inference. But this was like a new class of examples that you can exactly solve. So I was happy about that, although it's just linear in X, it's very nonlinear in its parameters. Okay, and the two things that we learned is that there's kind of a whole new world of scaling limits that appear when you allow the data set size to grow. So there's actually, it turns out, two notions of effective depth. So the L over N, of course, survives, and that's the effective depth of the prior that I basically discussed before. But there's a new notion of depth, which plays the role of the effective depth of the posterior that you get. And it's L over N, but times the sample size that you have. Okay, so let me show you the phase diagram rather than trying to talk through it directly. Okay, so here I am again, on the x-axis is the depth, on the y-axis is the width, and everywhere here the number of training data points goes to infinity. I just couldn't draw it accurately with the third dimension. Okay, so I'm going to give some names to things. This thing that I call the effective depth of the posterior, number of samples times depth over width, I'll call lambda, and depth over width I'll call gamma. Okay, so the first part of the phase diagram is way up here. This is the analog of the NTK regime, and it says, look, even if the number of samples and the depth went to infinity, as long as they went to infinity such that their product is smaller than the width, so lambda goes to 0, you still get back the kernel regime. You get exactly the same answer as if you had used just one Gaussian matrix. So that's kind of why I call it the effective depth. That's the parameter that if it goes to 0, you get the same prediction as if you had 0 depth neural networks. And so moreover, what happens is you get this kind of one parameter family of models parameterized by the limiting value of lambda that describes what happens is you get more and more and more nonlinear posteriors. Okay, so there's basically two interesting properties in this weakly coupled phase of learning. One is that the posterior depends only on the value of lambda that you chose and on some very coarse statistics of your training data, specifically the proportion of the directions you observed in your input space and the norm of the minimal norm interpolant of your data. Okay, so if that doesn't make sense, it doesn't matter. I'm just saying you get a kind of very simple one parameter family of posteriors you can write down explicitly here after doing asymptotics. But you learn the following thing. So I'll write it this way, that the evidence is never maximized at finite values of the effective depth of the posterior. So for those of you who aren't familiar with Bayesian evidence, so for a Bayesian, there's this really beautiful way if you give a Bayesian two models of deciding which model does it better, it does better at fitting your data. Okay, and that's to measure the evidence of the models. So this is basically the posterior probability of having observed your data to begin with. So this is like maximizing the evidence, like maximizing partition function. And this is actually the first time, this is the only place I know of which gives an exact mathematical reason to prefer deeper networks. So if you're a Bayesian and you believe in evidence maximization, you never want to settle for a finite value of this effective posterior depth. You got to go to infinity. That's just how the mathematics works out. Okay, so that's phase number one of these kind of deep linear posteriors. And then there's a second phase, there's a phase transition where lambda equals infinity, so the effective depth of the posterior is infinite, but actually the effective depth of the prior changes. So there's another one parameter family of models. And here you kind of have a strongly coupled regime. And what happens is you have a phase transition in the sense that here your posterior was changing for different lambdas, but here actually the posterior is the same everywhere. It's independent of the value of gamma you chose. So you get the universal posterior that maximizes the evidence. So it's if you get a good posterior, okay, but while the posterior is the same, the evidence actually is different. The posterior maximizes the evidence, but the same posterior appears for models that have different evidence. And there's a unique value of gamma, a unique ratio for the depth over width that depends on the statistics of your training data that actually maximizes the evidence. Okay, so I'm saying I wasn't expecting to find something so complicated for these deep linear networks, but this is basically a complete characterization of the phase diagram for Bayesian inference at 0 temperature with these deep linear models. And one of the things that we're finding, although I'm not going to present it here because my understanding is not as complete as I'd like, is that even for the nonlinear networks, it's really this notion of effective depth, whether you do stochastic gradient descent or Bayesian inference, that controls how far you are when your data set size is large from being a kernel method. So this is actually a useful kind of thermodynamic parameter, if you want to say it that. Okay, so let me pause again. It might be very difficult or potentially impossible to parse this diagram. If it's impossible, I'm going on to something else, so you can ignore it, but I wanted to at least attempt to present it.
So what's the best strategy? What's the best slope?
So the best slope, so there's a formula for it, and it looks like this. Okay, gamma star of your training data is the logarithm of, let's see if I can do this. Just the norm of the minimal norm interpolate of your data divided by alpha naught, which is the proportion of directions that your training data fills out in your input space. Let me see if I can do this right. I want to say +1. Pretty sure this was the formula. Okay, so the point is you get a formula, and it's completely explicit. It's like not completely obvious how to interpret it, at least for me. But it was like I was really happy to see something like computable come out. So that's the best. Yeah.
We're trying to just kind of overlay, extrapolate this to other kinds of models. With the capital N being more like the square root of the number of parameters, or the dimension of the variance.
Okay, right. Thank you. I should have said this. So typically L over N, the right generalization of it is it's the kind of sum of the reciprocals of the n's. That's how it usually works. So really the right thing to generalize is the L over N. And the number of parameters does not directly seem to enter in some natural way that I can see, with the asterisk that I don't know how to do this for
It's
the.
more like a dimension.
Yeah, that's right. It's more like I think of it, it's like in every layer I have like an n-dimensional representation of my data. Something of that. Doing well. All right. So very good. So let me, I have just a couple of minutes left, I think, right? 7 minutes?
Yeah, so.
Okay, great. So let me now return to the pictures I showed you in the very beginning, which were for ResNets. And just to illustrate, ResNets are easier actually than fully connected networks by far. So this is a setting we understand much better. And let me just say, this is the definition of a residual network. It's a little bit different than a fully connected network. Rather than starting with an input X and computing W times X, okay, here I've kind of done the correct normalization for it. You return the original input plus an affine transformation. That's what you do in the first layer. Then in the second layer, you try to learn the residual, the difference between what you produce and what you produce in the first layer, and you model it as a single layer like this, 1 over square root of the dimension times the depth. That's the thing which wasn't completely obvious to put in, but is the correct thing to put in retrospect, times a kind of single layer like before applied to the previous layer's representation. Okay, you do this capital L times, you have L residual layers, and then you have a readout of the model like before. That's my definition for what a ResNet is. Okay, so in the optimization procedure, okay, just to be precise, what we do is we do gradient descent, and it's a kind of known fact that you have to rescale the learning rate, or here the learning rate schedule. I'm allowing my step size to depend on t by a factor of the width. This is what's called the mean field parameterization or the mu-p parameterization of neural networks. So it's not completely obvious that you have to do this, but this is the right thing to do to get any kind of non-trivial learning dynamics And the question that I'm interested in this setting is, can I transfer this learning rate? That was at least the kind of practical side of it, the best choice of this A to T when scaling L and N. I want to make my network wider and I want to make my network deeper. Can I actually find the best learning rates in a cheap way? Okay, so the basic claim, and this comes from a theorem which actually in which we were able to characterize the kind of limit of these training dynamics as N and L goes to infinity in a somewhat horrible but completely explicit way, is that with this parameterization, when you have this 1 over square root of NL here, and this 1 over N here, and this N here, they were all necessary steps, then hyperparameters like the learning rate A to T, okay, we didn't really put it here, but things like the batch size, things like the momentum coefficient, et cetera, will in fact transfer when you change the depth and the width. Okay, so all this analysis for now requires a fixed training data set size, and all of these prescriptions break when the data set size goes to infinity. So the previous slide that I was showing you is like one of the very few times we have an exact analysis of learning with a growing data set size. That's why I was excited by it. Okay, so let me now go back to these hyperparameter transfer plots. So this is the one I already showed you. Okay, this is where the hyperparameter here, just the constant step size that we were optimizing over, transfers across depth and width. But let me show you another thing. Okay, the beauty of doing practical things is just because your theorem doesn't apply doesn't mean you can't run the experiment. Okay, so the previous kind of plots were for models that were exactly the ones we proved theorems about, just to make sure we didn't make a mistake. So, but here we did something that was actually quite sophisticated. We took a vision transformer with self-attention and batch norm and all the bells and whistles. And we kind of did our rescaling of everything. That's what this 1 over square root of L suggests. And we took a complicated cosine annealing learning rate schedule. That's what like people will typically do in practice. At least it's fairly common for computer vision tasks. Okay, and we did it on complicated data sets. We did it on ImageNet and we did it on tiny ImageNet. So these are like, okay, ImageNet these days isn't really considered realistic, but it's certainly more realistic than CFAR10. And the point I want to make is that although the models are very different and the theorem doesn't exactly apply, we were very pleased. We got very good hyperparameter transfer for the learning rate, both for tiny ImageNet here and for ImageNet over here. And we didn't run so many experiments here because it's pretty expensive to actually filter over all these learning rates. But it's not too bad. The depth changes by a factor of 3. This is the most we could change the width for kind of numerical reasons, but number of parameters scales as the square of the width. So it's like a fairly large change. And we found that even for these models where the theory doesn't directly apply, actually the prescription works perfectly well for the transfer. And so that made us very happy. And this is something I think people in practice are quite happy to actually use. Okay, let me pause for just 1 second and ask if there are questions about this. I have one more slide. That's it. So yes.
So just if I'm understanding right, I think the neural networks already use a 1 over root 10 normalization for
Yes.
So the new thing here is kind of actually normalizing with respect to the depth. Of the
Yes, correct.
Right?
Correct. The way you can think about it is if you've ever seen like a discretization in time of an SD, like the weights are random, right? So if I kind of go back for a moment. So at the start of training, think of the weights as being random. So this 1 over n is like, this is a big Gaussian matrix. This 1 over root n is the thing I showed you before, is the rate normalization. But it's like saying that the increments of your process, Z2 minus Z1 is like a Gaussian. And so this 1 over root L is like a kind of standard Euler-Maruyama kind of discretization of your SD. It's like 1 over L is your delta tau. That's how much your layer index is changing when you normalize by the total number of layers. But you have to normalize by 1 over square root, or like square root of delta tau, because it's like only a variance game that changes. So there's like some principled way to guess this, but then you actually have to take the limit and prove that things converge and all of this. So that's kind of where it comes from. Okay, I forgot to put one more slide about these numerics here. Let me say, like, you might ask, how much compute can you save? Do you really have to go out to 20 epochs? I kept the 20 here. I don't know why I wrote 20. Could you go out to 9 epochs or 3 epochs or whatever? And we didn't push this very hard in the paper because it wasn't clear how to ask it in a principled way. But the best learning rate you find after 9 epochs is the same as the best learning rate you find after 3 epochs. So there's like a lot of room to save a lot of compute. You want to have the smallest model that you train for the smallest number of epochs. That's kind of the game. And we're not sure how to characterize what the minimum is. For sure, it's data set dependent and so on. Okay, so let me just do one final thing. Okay, so I'm just recapitulating my model. That's my residual network. This is my optimization scheme. And I just want to make kind of what I think is an interesting point, just how you analyze learning in these ResNets or indeed in these fully connected networks. The point is basically that there's a symmetry group that acts. There's a symmetric group that acts on every layer. All the neurons in every layer are completely exchangeable in distribution, right? The fact that I called one neuron 7 and another neuron 12 doesn't actually make any difference. So the only thing that can matter are symmetric functions of the neurons in every layer. And in fact, what we realized, this is really the invention, I would say, of Cengiz and of Blake, who are here at Harvard. They did this in the fully connected case, but it carries over to the ResNet case, is that in every layer, you have to study two kernels. You have to study the kernel that recapitulates for you the statistics of the forward pass. So this is the kernel where you give yourself two different inputs, and you measure the overlap of the vector of representations that you get. And then you have to do the same thing, but with a slightly different normalization, just because this one has mean 0, for the backward pass. So you compute these Jacobians, the Jacobian of the output with respect to your representation in the layer at one input, and the Jacobian of the output with respect to your representation at that layer, another input, okay, normalized by root. So the point is you can basically write the statistics of training only in terms of the dynamics of these kernels. And at finite width, these kernels are fluctuating objects, they're random. But you can see that these kernels are just averages. And so really the thing to check is that these kernels self-average. They converge to their mean in the infinite width limit. You get the kind of, these are like the right order parameters to study if you want to say it that way. Okay, so I just vaguely stated the theorem. The formulas you get, the SDEs for these kernels are fairly horrible. But the point is that as n and L goes to infinity, these kernels basically satisfy an explicit evolution equation. They basically have two time indices. One is the layer index. It's like the proportion of layers you've gone through in the network that acts as a time index. And then there's the actual time of optimization. So like they're two variable kernels in this sense. And the only important part about this explicit evolution from the point of view of the hyperparameter transfer is that the learning rate schedule, the entire A to T, simply survives as a dimensionless order 1 hyperparameter in your limiting dynamics. And so although the limiting dynamics are very painful and really can't be solved, at least at the moment explicitly, what you know is that you chose the right parameterization to have your learning rate remain as a dimensionless parameter over which to optimize. And that's kind of the hallmark of being able to do hyperparameter transfer from my point of view. Okay, so let me stop